Welcome to a lesson with Dr. Pell. Let's look at some graphs of some um, functions that are written in cylindrical coordinates and spherical coordinates. Um, and to kind of get a feel between these variables and what they mean, the z, r, and theta. For instance, suppose that we had something like this. Um, Z, just like I have here in this code. So Z is equal to, let's see here. Yeah, Z is equal to something. Suppose that Z is equal to R squared. That's what this means. So Z is equal to R squared. What do you think that would look like? So R is the distance away from the Z axis, quite literally. It's just kind of like in polar coordinates, the distance from the origin, but you can raise that up and down. So it's the distance from the Z axis. So the distance from so z is equal to the distance from the z-axis squared. So you can almost think, if you just kind of think in this one direction, what happens? It kind of should look like kind of like a parabola if you just kind of look at one cut right here with an r value going either this way or that way, and the z value and the relationship would be kind of like y is equal to x squared, right? So as r increases, that'll increase z as you go, and it should work just like this as a parabola, but it's going to do it in every direction. So let's see what actually comes from that. Okay, so let's take a look at that. Push execute here in the code. And that's exactly what we get. So it's like a parabola in every direction. So z is equal to r squared gives us something like that. Let's look at another example. What if we have something like r? Like r is equal to 2. So r is equal to 2, meaning like this. So an equation like this, r is equal to 2, and we're working in cylindrical coordinates. So it's polar coordinates, but then with a z going up and down. So r is 2. What does that mean? So all the points, remember, r means distance from the z-axis. So distance from the z-axis will be 2. Well, think of the z-axis and going 2 in every direction out from it. It should give us a cylinder, right? The radius of 2, about where the z-axis is right in the middle. Let's see if that's what happens. All right. Okay, let's go for it. Push execute and see, and yes, indeed, that's what happens. We get a cylinder. Okay, so distance of 2 away from the z-axis. All right, let's look at another one. This one is, what if we had theta equal to something? So we're going to have theta equal, in this case, it looks like we're doing this right here. Okay, it looks like we have theta is equal to pi force plus, um, uh, we can write like this, pi force z. Okay, so interesting. So our angle is going to depend on the z value, all right? So when z is 0, it looks like the angle is pi force. So let's just think about that. So in the plane, z equals 0, theta being equal to pi force, all the points in the plane with theta being pi force, let's think about that. We have our x and our y-axis right here. Pi force is, so in the plane, xy plane, it's just going to be going that way and back and forth, just at 45 degrees. That's what we're looking at right there, pi force. And then as we move up a z value, once we get to a z value of 1, we would be at pi halves. So the angle would be actually going this way. So it's going to be kind of twisting, like a staircase almost. It looks like some kind of twisting action as we go. Let's see exactly what that would look like. Okay, so let's press execute and see that. And yeah, do you see the twist? So it twists, and then it goes. But one. We're only looking at one quadrant. It looks like because yeah, because um, or one half rather. Um, and these are octants, so looking at um, we're kind of looking at part of it. I guess two octants. We're not looking at it what's below. So this is like um, this is one part and another part as it goes along. But you can kind of see the twisting pattern that evolves from that particular equation. Kind of fun, kind of like a slide. It's a slide equation. All right. Okay. Let's look at the next one. Okay, so next we have spherical coordinates. Okay, so we have the different variables, phi and rho and theta. Okay, and setting these variables equal to different things. So for instance, let's suppose phi is equal to pi force. Okay, so we're going to be looking at an equation like that. Um, phi is equal to pi force. Now, what does this look like? Let's remember what phi is. If you look at the positive z-axis, phi is the angle from the positive z-axis. So we have pi force. So all the points that have phi being pi force, I mean, basically it's going to be everything in a cone like this, going off that way and that way. Like that, kind of just in this upper part. Let's see how that looks, if that's accurate. And let's execute this and see what we get. Okay, it looks like, yep, actually it only gives us part of the graph here, I suppose, because if you look at these z-values, the z-value only goes down to 0.71 and the y, so we're only looking at one part of the cone. Guess if we made the graph a little larger, we'd see more. So why don't we try to do that here? In fact, let's see if that's something we can do. So rho is going between 1 and 2. What's rho? Rho is like the distance from the origin. Why don't I change it from 0 to 2? And theta, that's only giving us 1/2 because theta is the spin about in polar coordinates. If you're only going to pi, you're only going halfway. So why don't we do 2 times pi, and let's see what happens now. And we get the cone that we desire. Just had to make sure we're kind of getting all the parts. So remember, and maybe we'll write this out here, that theta. So now the xy plane is what's down below here. And if we had, okay, x is 0 there, I guess we'd have to twist it. But let's just kind of imagine here that we have x-axis here and y-axis here. So theta is this angle that's made right here. R is this value right here. But in spherical coordinates, actually, rho, which is a Greek letter in place of R. So rho is right there, would be right in here, that length. I know it's kind of dark, but okay, it would be that length from there to there to a particular point. That, okay, so we have rho. So we want rho's going from 0 all the way up to 2. Theta is spinning all the way around here, 2 pi. That's why we get the whole rounded shape. And then, but here, why is it just the cone surface right here? That's because we set the phi value right here equal to a constant pi force. So phi value right here, so down from here to here, that's pi force, and it was constant all the way around. Okay. And suppose if we wanted to actually looking at this, okay, we're good. All right. Okay, now let's take a look at the next one. This is rho. So remember what rho is? Rho is the distance from the origin. So this right here, it looks like a P, but it's a Greek letter rho. Um, and so this is rho is equal to 2. Rho is equal to 2. And what does that look like? Rho is equal to 2. Okay. All right. Let's see this. We get a sphere. Distance from the origin is always 2. Look, we get a ball. We get a round ball here. That gives us a sphere. It's kind of fun. All right. Now let's take a look at the next one. This one is theta. So theta is equal to something. All right. So theta is equal to pi 6. What does that look like? So in the xy plane, theta equals pi 6. That would be everything on the line that makes an angle with angle of pi 6 here. So in the xy plane, angle of pi 6 going out this way. Now, if you allow for negative r values, you could go backwards if you were in polar coordinates. But right now we're in spherical coordinates. And I guess even for negative, that would be like negative rho, like going backwards the other way. So you go back and forth. But you should just get a flat plane going at that angle. Let's see if that's what we get. All right. All right, let's do this. Ah, we did it. It actually looks like a coin. Why is it rounded? That's because our rho value we set in the graph, the bounds for rho went from 0 to something. Let's see what that is here. Yeah, sure enough, or from -2 to 2 even. It went back and forth in both directions, especially since we're at pi 6, but in order to encapsulate back and forth, we needed to have negative rho values as well. And the rho value, the distance at most is 2 away from the origin, which makes a coin. So that's so that graph, but made into a coin. Okay, with those coordinates. So now what would happen if we change this rho value? So it would go from 0 to 2. Let's just experiment, see what happens. We get 1/2. Aha. Yeah, just as suspected, 1/2 of the coin cut in half. All right. So that concludes our little adventure exploring some three-dimensional graphs in cylindrical and spherical coordinates. Thanks for watching.